Welcome everybody to our webinar. So this is the second webinar in the series of webinar that we have prepared and are organizing about high performance computing, or HPC. By we, I mean not just Lux Innovation, but in partnership with Lux Provide and the University of Luxembourg. For those of you who don't know me yet from the first session, allow me to introduce myself. I am Ramona Caulea, and I'm working at Lux Innovation, the Luxembourg Innovation Agency. And today, we will see the second session about HPC and supercomputers. Regis, thank you for, you can register for the next sessions as well. But let me introduce the platform to you, the streaming platform on which are doing this webinar today. You can see that on the right side of the platform, we have a chat box that you can use for technical questions and also to introduce yourself, because we'd like to have this webinar as much interactive as possible. So don't hesitate to share your contacts so you can always also network with other participants on the platform. We have also the questions box. This is for the questions on the content. We will have a Q&A session at the end of this webinar series or webinar session. And don't hesitate to put your question there. We will take them and we'll try to answer the most of them. And we also have an anonymous poll that I would like you to answer as much questions as you can, just to understand to whom we are talking to, and so we can adapt our speech and our next sessions to your needs as well. So let's see the poll and the questions we have there. Let's see them together. The first one is, are you already planning to use HPC resources in your activities? The next one, if so, when do you plan to use HPC resources? In 1 month, in 6 months, 12 months, 1 to 3 years, 5 years, or you don't know yet? The next one is, for what would you use HPC? For simulations, for modeling, for big data analytics, for artificial intelligence, including machine learning and deep learning, for bioinformatics, or others? And the next one, we have more. For what would be your fields of HPC applications? So you can find different fields. If you don't find your field or your specific domain, you can also select other. Well, while you take your time to answer the questions, I will continue with introducing to you the concept of our HPC Thursdays webinar series. So for you who already followed and connected to our first session on the 20th of January, we discussed about the benefits of using high-performance computing to boost your innovation activities. If you didn't have the chance to connect 2 weeks ago, you can find the registration, so the replay on YouTube on Lux Innovation channel. Today we are going to see with Matti, and in a few moments I will give him the floor to introduce to you the supercomputers, how they work, and the basic elements that you should know before using a supercomputer and to use it efficiently. And then on the 17th of February, we'll have a session dedicated to simulations, why you should use simulations. And on the 3rd of March, we will see a dedicated session on artificial intelligence and high-performance data analytics. Then we will go into a much more focus dedicated to HPC use cases. We'll have an HPC use case example for health, other for digital history and public administration, and for finance. The last, but not least interesting and important one, session to discover the supercomputer of Luxembourg, Meluxina. So it's a unique business-oriented supercomputer and accessible to companies as well. So let's see the agenda of today. So today we're introducing supercomputers, and we'll see some HPC use case examples as promised for every session. And then I'll conclude with the National HPC Competence Center to give you an overview of the services and guidance available in Luxembourg for you if you're interested to approach to the supercomputer world. And we'll have also a Q&A session to answer your questions, so don't hesitate to input them in the Q&A tab, and we'll conclude the session answering your questions. So now I will leave the floor to Ezhilmathi, who will give you the basics of supercomputer. Mati, please, the floor is yours. I will just remove my slide and leave your slides to be published, shared. Okay, we can see your slides. Perfect. Now I mute myself.
Sorry, I think I was muted myself. Thank you so much. Okay, now I shared my screen. Hello everyone, good morning. So my name is Ezhilmathi Krishnasamy, and then today I'm going to talk about this introducing the supercomputers and then how to use them efficiently. This is going to be like a very basic concept. I'm not going to go into like a lot of detail because this webinar is just for like 30 minutes. So I wanted to cover like as much as possible concerning this supercomputing and then how to use them efficiently and so on. So I would also like to introduce to you all about my educational background. So presently I'm a postdoctoral researcher in high performance computing from 2019 in Luxembourg University. So I used to coordinate this Pre-6IP project from the Luxembourg University from 2019. I'm still doing that. And then from 2021, I'm also part of this EROCC effort from the Luxembourg University. That is why I'm doing this webinar now. My main research interest is applied mathematics and then high performance computing. Prior to my postdoc, I was doing my PhD at the KTH in Stockholm, Sweden, and also in Bilbao, Basque Center for Applied Mathematics in Spain. So my PhD thesis was about like high performance computing and then finite element simulations for CFD applications and so on. If some of you are interested to take a look at my thesis, the link is provided in the slide. So after this session, we will provide you this recording, plus also we will try to provide the slides so that you can click the link and so on, so you can see if you are interested and so on. So who can benefit from this webinar? As I mentioned before, this is going to be like a very basic element. So mostly we want to try to cover like a very friendly elements, not like go into like very detailed and so on. So basically the students from bachelor and master studies, early studies, the early bachelors, early masters, and then early stage researchers who is working with the mathematics and physics, because most of the time we don't think so much about this computers and so on, because we mostly focus on this mathematics and physics laws and calculation and so on. So for them also it would be quite interesting, so that they can use these machines for their science and research and so on. And also like public and private institutes who needs to use the HPC for their research activities as well, because nowadays it's very, very essential to make use of this HPC architecture, because it's getting like more and more popular. So it's like if you go back like 20 years or something like that, we don't use so much HPC for our daily activities, but nowadays it is like more convenient or more needed to use this HPC for our daily activities and so on, research and then production applications, everything and so on. And also, of course, it's not like everyone who can have their machine on their own or access to the supercomputers. Of course, some private sectors also, they want to use these cloud resources. But we don't know how we need to use these cloud resources for our application and so on. So this seminar will also give like a basic idea about this, how to use the cloud resources efficiently and so on. So what we are going to discuss today, so as I mentioned before, the HPC, the supercomputers are like more popular and popular nowadays. So it's good to know like the basic the architecture of these supercomputers. For example, like a CPU and GPU and memory and etc. Because those are like very basic elements. Of course, there are like low-level details, but we don't need to know about that. As long as if you know like the basic fundamentals, that is more than enough to use these supercomputers and so on. The second point is like understand your problem, because most of the time we use the supercomputers for like physics or biology or finance, mechanics, and data analysis and so on. We also wanted to know like how much resource we want, like for example, like how much memory we want from the supercomputer, how long do we want to run our application in the supercomputer, how many nodes. I will come back to these nodes, what it does mean later of this presentation. So afterwards, we also want to know like what kind of software is available in that particular supercomputers, because we have like our physics or biology or finance applications. At the end, we kind of like use some kind of like software package to run this software in supercomputers. So we also want to make sure that like, okay, I want this software to be available in the supercomputer so that I can use my input parameters in the software so that I can run my application in the supercomputers. There are like many well-known softwares that are available to support like data analysis, bioinformatics, physics, and biology. For example, like TensorFlow, GROMACS, ANSYS, OpenFOAM, etc., etc. And then the last one is, of course, most of the time we use like existing software, like someone develops the software and then you just put some parameters and then you run your simulations and so on. But also like to use these supercomputers very efficiently, like very low-level people. When I say low-level people, means they have like a higher knowledge of this supercomputing, programming, parallel programming, things and so on. So they also want to use like this MPI, OpenMP, CUDA. These are like a parallel programming, because when we say supercomputers, they are like a very powerful machine. To be able to use them like very efficiently, it is very, very essential to know this some of this programming language. Otherwise, we cannot use this, like your own applications and so on. Of course, if you're going to use like some of the softwares, it's okay. But if you want to run your own things on the supercomputers, then you should know any one of these languages to use the supercomputers. Mainly, you should know MPI, because MPI will give this scalability. That means you can access the entire supercomputer for your applications and so on. So why we need a supercomputer? So as I mentioned earlier, like nowadays, it's very, very essential to use the supercomputers for like science and research and so on. So I have listed out like just for examples. For example, in astrophysics, to simulate this the plasma things and so on, and then also this is CFD turbulence. It also needs like a lot of computational power, and then bioinformatics, and then material science to see this how this the properties of the materials changes with this bonding and things and so on. So these needs like a lot of computational power. So if you're going to do the simulations on your laptop, it's going to take a lot of time. But if you're going to do the simulation on the supercomputers, it's going to take like a very fast and so on. So I would just like to show you some visualization, but okay, I don't see it here actually. So later you can click once the slides are shared with you, you can click on this the blue highlighted color, then you can go through these nice videos and so on. Continuing with this previous slide, so most of the time in science and engineering, we need to do like a lot of arithmetic computations. For that, we need to have like a computers. And then all of these, the physics, physics phenomena are defined by the mathematics, by these partial differential equations. To solve these partial differential equations analytically, it's very, very hard. So we need to use like an approximation method to solve these PDEs, partial differential equations. So when we do these numerical methods, we end up solving this system of equations. Like we want to find the unknown variables from the system of equations. Then it will become into like matrices and vectors. So we want to like do this iterative process to find this unknown for the variables and so on. This not only applicable in science and engineering, plus also like in artificial intelligence as well. So most of the time we end up solving the matrices and vectors and so on. By to solve these things in a normal computer, it will take a lot of time, like in your laptop and so on. So that is why we need to have like supercomputers, so that we can solve these equations very efficiently, very fastly manner. So since the webinar is focusing on this Luxembourg HPC supercomputing platform and so on, so we also would like to highlight like what kind of HPC facilities in Luxembourg we have. So basically, we have like 3 supercomputer machines in Luxembourg. The most powerful one is Meluxina, which is controlled by this Euro HPC and the Lux provide. And then Ion and Iris is controlled by the Luxembourg University. So I just highlight like a few things, like the CPU architecture and GPU architecture and so on. And then the vendor is like AMD and Intel. So they are like different chip manufacturers of these CPUs and so on. And then the GPU is also like it's NVIDIA. Some of you might have heard somewhere else like NVIDIA and so on. So it's like accelerators, so that you can run your applications more in parallel along with these CPUs. So this is a nice, interesting plot, because each and every year the power of the computers are like increasing and so on. So there is a web page who is like maintaining this database. It's called like a top 500 org. So they always like highlight like the topmost supercomputers around the world and so on. And then the first line, the topmost line, the green line, it shows like the sum of this top 500 supercomputers total power. And then the middle one, like the orange line, it shows that the topmost power, number one supercomputer power, the computing power. So you can see like almost like 100 petaflops it's going. And then the last one, the 500 supercomputer, it falls into like 1 petaflop and so on. So it shows like clear indication that like the power of the supercomputers are like going forward and increasing over the years. So that we can also use our applications using this supercomputer and so on. When I say this, I also put this flops, that is like floating point operation per second. That is a kind of like a measurement that measures this power of the supercomputers. So that's how we measure like, okay, this can do like this much fast computations and so on. Of course, the power of the supercomputer is like increasing over year and year. But also we also we are also very curious, like, okay, where it has been used, like in which sectors are using most of the supercomputers and so on. So again, this the top of 500 org, they are kind of like documenting this database. For example, like in the left-hand side picture, you can see research uses like a 26% of this supercomputer resource and so on, and then IT services, and then you can see like aerospace, or energy, or weather, or climate research, and so on. They're also sharing this part of this system and so on. These are like a worldwide system, not only just like in a particular area and so on. And also like in the right hand side, you can see the picture, like these are the accelerators, which kind of accelerators are like a part of these HPC machines and so on. Because some years ago, the supercomputers, they used to have like a only CPU based machine, but nowadays most of the supercomputers are like heterogeneous architecture. So when I say heterogeneous architecture, that means they are composed of like CPUs and GPUs together, or some kind of like accelerators, for example, like FPGAs, in Melixena in Luxembourg, and they have like two kind of accelerators. One is the GPU accelerators, plus also they have like FPGA accelerators as well. So it's good to know, like, because once we know these kind of things, so then we kind of like aware how to use our applications. Okay, in this machine I have like this CPU and GPU so that I can use this application, or maybe I need to program this way so that I can use both of these things and so on. So that is an idea to share this information here. And then I just want to give like a quick overview, like a difference between the laptop and supercomputers. It's just like a very quick. So, you know, like a laptop has a few cores, supercomputers has like a lot of cores, like many cores and so on. Laptop has like a limited memory, but supercomputer has like lots of memory. Laptop is slower than supercomputer, and then supercomputer is faster than laptop. In laptop, you can have like your personalized operating system, but in supercomputers mostly have like Linux based and so on. The laptop is owned by you, and then the supercomputers are mostly owned by the public sector, and then they are located somewhere else. They don't locate near to you and so on. The laptop is used only by you, but the supercomputers can be used by many users. Not only you're going to use the supercomputers, many people are going to use the supercomputers and so on. You can see the pictures also in the right-hand side, like a lot of laptops are connected to this many computing powers in the supercomputers and so on. This is just to give you some illustrations, so to give an idea and so on. So now we are going to look into this, the architecture of the supercomputer, how it is designed. Most of the supercomputers, they have like compute nodes, and then each and every compute nodes are connected to each other and so on. So each and every compute node, typically you have like two sockets, and each and every socket you have like many cores, and then they are connected together. So each and every node can have like 24 cores or 36 cores and so on. And then each and every node, they're connected to each other via this network cable. It is called like InfiniBand or Ethernet. The right-hand side topmost figure, you can see the cube formulation. You can see like the small cubes are like one compute node, but then if you see the 3D dimension of this in z-axis, you can see like the cube is increasing. So that means like there are like many compute nodes. They're connected to each other via network and so on. So this is basically the supercomputer architecture. In a simple way, imagine that you have like your laptop, and then you connect like one laptop to another laptop. It can be like 1,000 laptop or 10,000 laptop and so on. So, and then if you can use them for your simulations, so how it can be fast and so on. So that is a basic idea. Of course, this is a very simple illustration, but it has like more technical detail. But yeah, so. And then one more thing, each and every node, they have their own memory. So this is quite useful when you want to run like simple example cases or simple simulations and so on. And so this is quite useful for that. So yeah. And then we have like these GPU accelerators in the supercomputers. As I mentioned earlier before, some years ago, we don't have like accelerators in the supercomputers, but now we have like a GPU accelerators in the supercomputers, because when we run the simulations, we can just like offload some of these computations to the GPUs, so that GPU can also participate in the computations along with the CPUs and so on. And then the GPU has like many cores compared to the CPU, but CPU is more powerful than the GPU. That means that the frequency of the CPU is more powerful than the GPU. That means they can do like really fast computations, but yet they cannot process many data in parallel compared to GPU. So that's why we can use the GPUs to process like many data in parallel and so on. In the GPUs, the GPU cores are like called together. It's like GPU processing clusters, and then each and every cluster, they have their own streaming multiprocessor and texture processor clusters and so on. So this I will show like in the next slide. So this is one clear example. In the right-hand side, you can see like a difference between the CPU and GPU architecture. You can see the green ones are like cores for the CPU, whereas on the GPU you can see like a lot of green boxes. That means like you have like many cores and so on. And then in the left-hand side picture, you can see the Volta architecture. This is one kind of architecture from NVIDIA. You can see like they have like a huge boxes, that is clusters, like 6 clusters. Each and every clusters, they have like streaming multiprocessors. So yeah, they are like very powerful. Like they have like many GPU cores and so on. Again, once the slides are shared with you, you can go through this the demonstrations, which is very quite interesting to see. The video link, and also like you can also see some technical information about this architecture if you're interested. So far we have seen the basic idea of the supercomputers, and then the how it is organized, and then the accelerators and the supercomputers and things and so on. Now we want to use the supercomputers. So how do we do that? So first of all, we need to connect to the supercomputers. To connect to the supercomputers, it's called like a workload manager. So this facilitates, as the end user, you can connect to the supercomputers. So not only they facilitate to connect to supercomputers, plus also you can also schedule your jobs, because you want to tell the supercomputers, okay, I want to run these applications like this many hours, I want like this many CPU cores, this information and so on. You can also monitor like if your job is running properly, or it has been canceled, or things and so on. These are like very, very essential information you're supposed to know to access the supercomputers. Otherwise, you might be left unanswered with a lot of questions and so on. So yeah. Yeah, they have like a lot of basic commands. Yeah, they have like lots of more information, but the basic few commands are enough to connect to supercomputers and run your applications and so on. So once we connect to the supercomputers, we also want to run our applications, the software. So we should know like what kind of software we want to use in supercomputers. Because if you do not know what kind of software we want to use, then it won't be quite useful. Most of the time, the softwares are installed by this particular supercomputing administrator in the center. For example, like ANSYS, OpenFOAM, Abacus, Chromax, and so on. Mostly it is done by this L-mode environment using this easy build. But as the end user, you can also install your own software using this easy build. But that could be quite challenging. So that's why I put the link also. If some of you interested, you can also take a look, and then you can learn more thing about this easy build and so on. So now we've seen that like, okay, we can connect to the supercomputers, and then we can use our application software, put the input parameters, and then run the software. The most important thing is whenever we try to run the simulations, whenever you use like, for example, if you use like TensorFlow, if you use like ANSYS, OpenFOAM, or Chromax, and so on, because most of the time we know that like, okay, the supercomputers is going to do like really, really fast computation. So that I just going to use like a lot of nodes, a lot of cores, very small time and so on, or maybe use like more time. So it doesn't work like that, because most of the time, as I mentioned before, the supercomputers are used by many users and so on. So the more resources you ask, most of the time you will be put into the queue, so you have to wait. It's better to try a simple problem in a small resource on the supercomputer on your laptop, and then make sure that this is working. And then once it is working, and then you can increase this computational resources, for example, like the memory and the CPU and GPU cores, and then the wall time, how long do you want to run these applications and so on. So this will be more useful, because if you try like new things and then you ask for a lot of resources, you will be put into the queue maybe 10 hours or 12 hours. After that, once your job is started to run, it might fail. Then you simply like wasting the time, a lot of time, like 10 to 12 hours and so on, waiting, and then the problem crashes and so on. So it's always good to try like a simple problem and asking like small resources, make sure that it's working, and then you can go for like a larger problem with a larger computational resource, like more CPU cores and then wall time, memory, and so on. To support this idea, so we can see like CFD example. The CFD problems are like solved by typically like finite volume or finite difference and finite element methods. Typically, it consists of like pre-processing, simulation, post-processing. So when you do this, the mesh creation and things and so on, like in the right-hand side picture, you can see like some of the examples, like you can see like Formula 1 cars and some tire simulations, wheel simulations, and things and so on. So when we do these applications, you have like lots of degrees of freedom. For example, like in this example, like if you have like 10,000 degrees of freedom, as I mentioned before, like, okay, I want to run my CFD simulations very quickly, like fraction of seconds, but your problem size is very small. So if you ask like a lot of resources, memory, and then the wall time, or CPU cores, then it will not run, because it will crash, because each and every the processor should have like a sufficient amount of the computational task required. If they do not share like a sufficient amount of the computational task, then the problem will crash. So in the bottom picture in the right hand side, you can see like the computational domain is distributed by these 6 cores, like each and every color represents 1 core and so on. You can see like 6 pictures here, because each and every time, of course, the shape might, the distribution load might change, but they are like more or less very equal to each other and so on. So in this case, if I use like 20 CPU cores or 200 CPU cores, of course, the CPU cores doesn't have like enough computational load to compute or to share this information between the cores. So then the problem will crash and so on. Because this is in the early stage, when I started to use the computers for my research activities, I have done this mistake. It took like a lot of time, like because it's working with the laptop, it doesn't work with the supercomputers and so on. So always try to run this simple problem with less resources, and then make sure, try to get some idea. Okay, if I have like this much data, I need like this much computational power, like memory and so on. This not only applicable in CFD examples, this also applicable to data analysis or bioinformatics, all the application, because the computational load should be properly shared between the CPU cores. If they do not share properly, then the problem will crash, and then probably you think that like, okay, this is working in the simple case, why it's not working with these larger cases and so on. So try to increase this computational resource gradually as you increase with your computational task, like for example, in data analysis and CFD and things and so on. So far we have seen the basic introduction about these supercomputers, and then how to connect them, how to run your applications using this existing software, for example, like TensorFlow, things and so on. But also, like, we also want to use like really, like a very efficient way of the supercomputers. Then we need to know some of the programming technique in the supercomputers. When we say programming the supercomputer, that eventually implies to this parallel programming technique, because supercomputers are based on this parallel architecture. That means we can run our application in parallel. So there are like many parallel programming techniques available to use these supercomputers. The most important one is message passing interface, because this will utilize all the computational resources in the supercomputers and so on. And then the second one is a shared memory programming. This is quite useful if your application is like very small. Of course, yet it's going to be like powerful than your laptop, but it's not like powerful compared to MPI message passing interface and so on. And then the third one is accelerator programming. So if you plan to use the GPUs and so on, you should know this any one of these programming languages, either CUDA, OpenACC, or OpenCL, and so on. Then the last one is very interesting ongoing efforts. It's like SQL and then one API. So this is like unified programming language that can be used for like any kind of heterogeneous architectures. So you don't need to think so much. Okay, if I want to use GPUs, maybe I need to write this SQL code. If I want to use the CPUs, maybe I need to use like different programming language. But if you use any one of these SQL or Open API, so they're going to be they're gonna use like a heterogeneous architecture automatically. So you don't need to think so much. So I will also give you some quick detail about these things, each and every programming model. So as I mentioned before, this MPI programming model is used for this distributed memory. So that means each and every node, they have their own memory, own CPUs and so on. And then they're well connected to this network, InfiniBand and Ethernet. To be able to program this, the entire supercomputers, we need to use this MPI programming model. So they have like many compilers. The compiler means as humans, we write the code, and then it has to be converted into understandable computer language, because whatever we write on the program, the computer doesn't understand. The computer only understands with the numbers and so on. The compilers will encode your human written code into understandable computer code and so on. So there are like many vendors, they provide like to convert your MPI programming into machine readable code. So as I mentioned before, this MPI program is quite useful to use this entire supercomputer computational power. This can be used in like in many applications, for example, like CFD, computational fluid dynamics, brain simulation, biomedical, material science, and things and so on. And then another one is OpenMP, and then POSIX threads. POSIX threads are like a very low level, and most of the times people don't use it. But OpenMP is like quite useful. So this can be used on the single compute node. As I mentioned, nowadays the single compute node can have like up to like 36 or 64 cores and so on. They have like a large memory as well, like 64 gigabyte or 128 gigabyte, depends on the supercomputer that you're using. They also have their own compilers that you should use them to when you program them. So this is like fairly simple to use this one. If you know how to do this serial code, like if you know C++ and C or Fortran things and so on, you just need to add like a few more OpenMP directives, like a few lines, and below this some of the areas in your code, then it will run in a parallel and so on the single compute node. This can also be combined with the MPI. That is called like a hybrid programming. So that is more like a very low level. So if you're interested, you can also take a look later. The third one is the CUDA and then OpenACC and OpenCL. So as I mentioned before, this GPUs are like the accelerators are there to accelerate your application. Like you can offload some of your computational tasks from CPU to GPUs, and then you can run these things and so on. Of course, to use these GPUs, eventually we have to learn some of the GPU programming language. So it doesn't work with just like a CPU programming language. So there are like a different programming model are existing to use these accelerators, and well-known, mostly widely used programming languages are like CUDA, OpenACC, and OpenCL. CUDA is like license-based. It's only applicable on the NVIDIA GPUs, and then OpenACC can be used on the NVIDIA and then AMD GPUs as well. OpenCL is like a very low-level language. It can target like FPGAs or AMD GPUs or NVIDIA GPUs as well. I would say that like I use OpenACC as OpenACC CUDA. I haven't used the OpenCL that much, but OpenACC is like a very fairly to use. It's like if you know OpenMP, it's very similar to OpenMP. It's most easiest language compared to CUDA and OpenCL and so on. If you're like interested, you can also follow the course. We also provide this MOOC online course from the press concerning about this CUDA and then OpenACC programming techniques and so on. So this is like the last one is a SQL and One API. the SQL is like a single source code. Like you don't need to think so much. Okay, you just write like one single code that can be used for like both the CPU and GPUs and so on, or any other accelerators like FPGAs and so on. So this will minimize the programmer's effort to think so much. Okay, I want to put like this much this computation on the GPU. I want to put this, but this code like automatically scale the entire computation on this given heterogeneous architecture and so on. I haven't personally used any of these ones, SQL one API, but I think they are getting more and popular. So it's also good to focus on these things so that you can run your application like research or your applications like production application things using this any one of these programming language. Similar to SQL, the one API as well. It's from the Intel effort. So they also say that like. It can target like both the CPU and GPU, and then any other accelerators and so on. So Intel is also going to they're also producing their own GPUs and so on. So if the supercomputer is going to have like Intel GPUs, of course this one API is going to be quite useful. Other programming language, of course, some of the previous languages I listed out, those are like a very low level language. When I say low level language, means you need to have like a lot of knowledge to do this programming and so on. But these are like high level languages. Most of you probably might have seen or worked on this Python and MATLAB and Julia. So some years ago, you cannot use them for this. You can only use them for like only serial version, like serial code. But nowadays, Python, MATLAB, and Julia, they offer like a parallel programming techniques. So if you know like a serial version of a Python and MATLAB and Julia, you just need to focus like a few more things, and then you can run this your code on the supercomputers using the parallel architecture and so on. It's not like a very complicated and so on. So it's you just need to know like a few lines, and then the execution of the program will use this entire application, the entire resource that you were asked for to run the application and so on. Julia is very similar to MATLAB. It's like a scripting language. It's also getting more popular. So yeah, so it's open source as well. So yeah. Finally, of course, we've seen that like, okay, we can run our applications and also we can program ourselves to use the supercomputers. But most of the times, we also want to make sure that like, okay, if I'm using this HPC resource in an efficient way, so there are like many tools are available to see to analyze your applications if I'm using properly or not, and so on. For example, like ARMForge, Intel VTune, Intel Advisor, and things and so on. They will give you, okay, if I ask for like 2 nodes with this much cores, and then you run applications, and sometimes they don't use like all the cores that you asked for. Maybe they don't use like enough memory and so on. And then you can also see the bottlenecks in your application. Okay, this code runs like most of the time in a serial version. It doesn't run in a parallel. And then you can go to this particular section of the code, and then you can try to change it and so on. So this information, if you're going to use any one of these tools, they will give you like a nice graphical visualization of this, where your problem is spending more time, where you can optimize and things and so on. So I also listed out like 2 more the documentation. They covers like entirely from A to Z of all this optimization and then performance techniques of this modern process and accelerators as well. So if you're interested, you can take a look and so on. Finally, the other interesting HPC developments is edge computing and quantum computing. So the edge computing means like you try to process your data very close to the place where you are producing. For example, it can be like drones, or it can be surveillance cameras and so on. So these are like these data are like handled by this embedded architecture. So they're like nowadays they're like very powerful than the normal laptop and so on. Sometimes you produce like a lot of data in a continuous time manner. That means you need to have like larger computational power and then resources and so on. In that case, this will go into like a small supercomputer somewhere else, very close by to this area. In that case, you need to use like any one of these the programming language or application software that we mentioned before and so on. So this is very interesting to know. So edge computing is a different name, but underneath somehow when you want to process like larger data, you will end up into supercomputing environmental things and so on. And then the second interesting fact is the quantum computing. It's one of these ongoing in development. I think in the near future we're going to have like a quantum computers, but meantime we have also like a noisy intermediate scale quantum supercomputer. It has been already being used in some applications. Some of the vendors also providing these services already. For example, like D-Wave, IBM. And then in Ulysses Supercomputer Center, they have this module called like Unique, where they couple like different quantum computers with their HPC machine. Because as I mentioned before, like large scale quantum computers, we can consider them as a future possibilities, because right now there is a problem with this error correction in the quantum computing, because they are defined by these qubits and bits and qubits. So when the quantum phenomena, when you test the qubits, they make some error. So this is like ongoing research how to minimize the error. Whereas in the classical computers, we have like a bits, like we can either get like a 0 or 1, but in a quantum computers, it's not the case. So that is why meantime we can use this quantum computers as like accelerators. So like you can just run like few computation on the quantum computers, and then maybe you can send these computers back to the CPU and then try to minimize the error. So in that way it can be used. So there is a lot of ongoing effort in this area as well. Finally, the key points. So we have seen so far like the basic understanding of this HPC architecture. So try to understand like the HPC machine that you're about to use, because if you don't have any clue about this HPC machine that you're going to use, that means you're not going to use like properly and the hardware resource that you're going to use or going to ask for it and so on. You don't need to know like so many things, at least basic like basic architecture. That's more than enough to run your applications and things and so on. And then choose like appropriate application softwares, and also familiarize with these job scheduling techniques, because most of the time you might make mistake, like you don't know how to ask resource, like for example like a CPU cores or memory or wall time and things and so on, or how to connect, how to monitor with jobs and so on. It's not like a lot of commands. It's like maybe 10 to 15 commands. Then you can easily handle these supercomputers. And then the most important thing is always try to run the simple test cases. Don't ask for like a lot of resources from the beginning. So that might be a problem. You might lose a lot of time if something crashes and so on. The knowing basic parallel program languages are advantageous, because if you want to use like efficiently supercomputers in the future for your research and things and so on, it's very, very important. Plus also, as you can see, like even normal laptops, they have like many cores. They are in parallel architecture already and so on. So in the future, I think no one is going to do like serial code. Everyone is going to do this parallel programming and so on. So it's good to know these parallel programming techniques and so on. Finally, try to understand try to optimize your application. Of course, when you run your application, when you write this parallel programming, you might think that like, okay, I have written like a very optimized code, but most of the time it won't be like that. I mean, anyone can write the parallel programming, but the most important question is how efficient your parallel programming is going to be and so on. So there are like many tools. Try to familiarize with those tools, and then try to optimize your code if you see somewhere else like it's not like optimized and so on. Thank you for your attention. So this is a very basic introduction, but if you click my name, you can see what I'm doing in the research and so on. So in case if some of you interested with this research and education collaboration, you can always contact me and so on. Thank you so much for your attention.
Thank you, Matti. Thanks a lot for your presentation. So I would remind you from the public, do not forget to take a look at the poll. We have new questions there, so we'll ask you to evaluate how much difficulty you found this session, so we'll be able to adapt for the next ones to your needs and to your interests. And don't forget also the other questions that we are having the poll tab. There again, it's a way to understand who are our public, to adapt our speech, to adapt the level of difficulty to your specific needs. So we have also some questions, but first I will present you 2 use cases examples, as we promised to do for each session. And as you asked last time, we will provide also sustainability use case. So don't hesitate to ask for what you would like to see as HPC use cases examples for the next sessions. We'll be happy to take your inputs and to respond to your curiosity. Another thing, don't hesitate also to ask us what you would like to know more about HPC and supercomputer for the next sessions, and we will do our best to respond to your needs, your interests, and what you'd like to see or to know, to learn more about HPC. So I will just present you these 2 examples of HPC use cases. The first one is about HPC for production optimization. This was an SME in the dairy sector that wanted to reduce the break time of their machines, because for each machine that breaks, it costs around 11 million euros per machine and per year. So whenever you have 3 to 5 times per year that machine breaks, you have huge costs. So using the HPC, this SME was able to develop a predictive maintenance software as a solution to reduce the break time of the machines. What was the impact of using using HPC for their business? Well, they increased productivity, first of all. Then they reduced the contamination of the environment when this machine were broken. And also they reduced the food waste, around 200,000 bottles of milk saved per year. And they had also, in addition, savings in the range of 50 million that they wouldn't pay as fines for breach contracts and not provided service. Let's see the second one. So here we have an example, HPC for sustainability. We see another SME because the Fortissimo for Euro HPC, it's a collection of HPC use cases examples that come from SMEs who applied HPC to their business. So you see every kind of size of company can use HPC, and not only companies. What was the problem here? So this SME core business is to design water turbines, so tailored to different environments, to different sizes and power. So the current practice they had before using HPC is to design these hydropower plants using empirical design, so with time-consuming experiments. By using HPC, they were able to customize and these power plants very fast and in a very reliable way. We see that the business impact was huge. They reduced the design time of turbines from 1 year to 3 months. This is remarkable. And in addition, they reduced the operational costs and augmented the efficiency of the plant by reducing the maintenance time. And they were also expected a market share increase by 5%. So this is translated into additional profit of 50K per year. So as you see, there is a huge potential and huge advantages by using HPC. You just need to find how to apply to your business and how to take advantage of HPC. So as we are running out of time, I will just rapidly go through the services available in Luxembourg. And then we'll go to the Q&A session where we can answer your questions. So we have the National Competence Center in HPC in Luxembourg. It's your contact point for high-performance computing and data analytics. And we are part of the European network. So we can rely on European network of other national competence centers. So who is behind this National Competence Center in Luxembourg? There is Lux Innovation. There is LuxProvide, who manages Meluxina, the national supercomputer, and is focused on industries and SMEs, offering tailored support to HPC use. And there is also the University of Luxembourg, offering education and training. So we want to provide not just the supercomputers, but the ecosystems to support optimal use of the resources through operational support, financial support, to R&D capacities, and to connecting you with other initiatives. We offer a wide range of services, from business support to identify the opportunities where to apply your HPC to your activities, to technical support from proof of concept, access to infrastructure, to HPC infrastructure, and support to use it, and the skills development with training, hands-on labs, and customer and domain-specific workshops. The European outreach allows us to connect you with other European HPC initiatives and to help you find international collaborations. So don't forget, your single point of contact is Lux Innovation, and we'll be more than happy to help you to get access, to understand how to use HPC, and to help you to access this powerful machine. So let's go to the Q&A session for answering your questions. We'll do our best to respond to the maximum of your question. Thank you. Thank you, Matti, for answering some of the questions in the meanwhile.
Yes, yeah.
Appreciate it.
So perhaps, can we take the questions?
Yes.
Thank you. Yeah.
So what do you mean by efficiently? So this is for you, I guess, when you speak about efficiency.
Yeah. So what do you mean by efficiently? Okay. So as I mentioned, like anyone can do this parallel programming, because writing the parallel program is not like a very super hard and so on. You can write like a very basic parallel programming. But if you do that, then that means you don't use like your hardware properly. If you don't use your hardware properly, then you lose all the resources, time and money, and then everything. So it's always good to know like very good understanding of this parallel programming, so that you can use these supercomputers efficiently. This is just like a programming perspective. Plus also, when you use like a TensorFlow or any other open form softwares as well, you need to know like few parameters technique, like tuning parameters technique, so that you can use these machines very efficiently. Otherwise, perhaps you ask more time, but you don't use them efficiently and so on. So that is my point. Yeah.
Good. Then we have a question about have any pricing strategy? Do you have any pricing strategy to compare with cloud?
Yes, because as you know, yeah. So when you run your simple cases, you like if you try like 2 to 3 times, you kind of know like, okay, for my application, I need like this much time or this much resource. By knowing that, you can, because the cloud providers, they might have already listed out the prices. Okay, if you're going to use like this much timings or this much hardware, you have to pay for this one. By knowing your requirements, and then you can see the pricing strategy and so on. So yeah. So it's always good to know your side, how much resources you need. Once you know that one, then you can see the prices in the cloud providers. Yeah.
May I add that if you'd like to know the prices of LuxProvide, They would like to set up a meeting with you and to understand with you how much resources you need, so they can offer you a more precise estimation of how much it would cost for you to use Meluxina. So in case you are interested, don't hesitate to get in touch with me, and I will put you in contact with the right person that could do your estimates. The last thing you should know about prices is that it's competitive in comparison with the cloud. Let's go to the next one. How do you evaluate your hardware requirement and time needed?
Yeah, so as I mentioned before, like you need to run like a couple of simulations. Either you run on your laptop and so on, because most of the laptop nowadays, like they're very powerful, like they have like a 4 cores, 8 cores, and so on. Or else you can go to the supercomputer, like ask for like small resources, and then try to run like simple cases, and then try to gradually increase your computational domain task, so that you can know, like, okay, if I increase this much computational load, that means I need like this much of the hardware resources, timings, and so on. I think if you run like a couple of simulations, you might have like a rough ideas and so on. Based on that, like, you can ask for the enough hardware resources.
Good. Thank you. Let's go to the next one. Is it possible to use HPC without any programming?
Yes, of course, you can. If you do not know parallel programming, it's okay, no problem, because most of the softwares, like, for example, like in a TensorFlow, things and so on, you just need to put the parameters underneath. They can utilize this parallel architectures and so on. So you don't need to think so much. But I think you need to know like very few things, like, you need to use like some tools so that they can be parallelized on this architecture, supercomputer architecture and so on. Of course, it is possible, but I wouldn't say that it is advisable, because in the future, somehow you might need to do parallel programming. So knowing parallel programming is always advantageous and so on.
Thank you. Yeah. Nice to know that you can use softwares to get acquainted with the machine first.
Yeah.
So it is possible to use any of the supercomputers in remote for free?
Yes, if you're like belong to the academic, of course. For example, me, I'm an academic. I can use these supercomputers from Luxembourg University, both Ion and Iris. So of course, I don't need to sit next to the supercomputer machine. I can also sit in. I live in Luxembourg. I live in Walferdam, so the machine is in Belvoir, so that I can use for connecting from my home to here and so on. So yeah.
Yeah, so you are using the HPC of the university for research purposes.
Yeah, exactly.
But if you would not be part of the university and using it for the research, of course, it's much more complicated.
Yeah, exactly.
I mean, not complicated, but it's not for free.
It's not for free, and then either you have to go to Meluxina or cloud providers and so on. So you have to pay for that. Yeah.
Yeah, exactly. So this is more, let's say, technical question. I would like to see a LES fluid dynamic simulation, preferably coupled with physics with heat transfer.
Yeah, exactly. So I was thinking that I can show some videos, but somehow the links doesn't work here. I'm sorry for that, but the slides will be shared later with you for participants, those who are registered. So if you click the links, like the blue highlighted text, and then they will open up like nice videos, YouTube videos. Unfortunately, I don't have any example with the heat transfer, but I have like 2 examples that are concerning about this turbulence phenomenon and so on. One is like an aeroplane simulation, which is quite interesting. I hope you might like it. Another one is the dam breaking simulation and so on. So both are like very interesting to see and so on. Please take a look.
Okay, we'll send you the slides and these links. Yes. Let's go to the next one. We have 2 more, and then we can conclude. If we want to master parallel programming and optimization to have very efficient code, shouldn't we first of all not use MATLAB?
Yes, the MATLAB is like, for example, like if you come from like a core mathematicians or physics and so on, most of the time we don't want to think so much like HPC and things and so on. We just want to run our applications, like, because our main focus is to crack this physics and mathematics. MATLAB is a very efficient tool. It's like there are like a lot of functions are built-in functions. You don't need to think so much. You can just do like matrix multiplication things and so on. Somehow, like the people, those who are working in MATLAB, they can be able to parallelize your application on the supercomputer. So if you do not want to spend more time on like coding or thinking, I think MATLAB or Python or Julia is like most suitable one and so on. So, but if you want to write your own code, like, your own syntax, Python or Julia, then you should know some parallel programming techniques and so on. So yeah.
Thank you. So the last one, to run small applications and to compare cloud vs HPC, any free trial runs are available, and if so, where, and he specifies is not in academics. So how could we try out how to understand how many resources we need?
Yes. So in that case, if you do not have access to the any HPC machine and so on, I believe that you can run the simulation on a computer. You can get some ideas, and then you go to the cloud providers, and then initially you can ask for the small resources, and then you try to run your application with the simple cases. Once you know like everything's working properly, then you can ask for like a larger resource in the cloud providers, and then you can try your bigger problems and so on. So yeah.
Well, thank you. That was all. We are now a little bit out of time, but hope you didn't mind. We try to answer all your questions. And if you haven't done so, please go to the chat and evaluate the level of information provided during today's session to understand better if we reflected your needs or we'll be working more to adapt to your needs for the next sessions. So I would like to conclude. Don't hesitate to register for the next session. Will be on the 17th of February, 2 weeks from now. We're going to see the power of simulations. So why should you use simulations into your activities, to improve your activities, to do it much faster and much easier. I will share my contacts here, my contact details. So if you are interested to know more about HPC, if you would like to speak to someone to understand your HPC requirements, HPC resources that you may need to use the HPC, or you'd like to speak to someone, some HPC expert, or you'd like to know more about Meluxina and the prices, as you have asked. Please don't hesitate to get in touch with me. I will do my best to respond to your questions, to answer your needs, and to put you in contact with the right person. I will thank you again for staying with us until the end. I thank you to Matti for presenting today.
Thank you so much.
And
it's a pleasure.
See you on the 17th of February for the next session, the same time, 11 a.m. on Thursday. Thank you.
Thank you. Bye-bye.
Have a lovely day.